In this last module of Chapter 5 on basic population models, Module 5.6, I will describe 9 basic properties of populations that emerged from the Lotka and Leslie population models. These include age structure transients, convergence to stability, independence of initial conditions, fertility and mortality effects, changing schedules and unchanging structure, age structure determination, reproductive timing effects on R, that is intrinsic rate of increase, speed of convergence, and population momentum. The first basic property is age structure transients. Short-term transient variation in age structure and growth rates will exist in populations with either fixed or variable vital rates. Oscillations of both the growth rates and the age structure will occur as the current newborns reach maturity and a new surge of births occurs. Populations are indistinguishable. A population growing with fixed schedules, which has not yet converged to a stable state, may produce patterns that are virtually indistinguishable over a short period from those produced by a population subject to variable schedules. A second basic property is convergence to the stable state. Decomposition. Population dynamics decompose into a growth process and a smoothing of the initial birth sequence over generations that forces the age composition towards a limiting form. The process of smoothing will average out the peaks and troughs in the birth sequence, which in turn will point both the age structure and growth rate towards a steady state. The ergodic property of losing information of the past shape of the birth sequence and thus the age structure emerges. Once the birth sequence reaches an exponential increase, the age composition must assume its stable shape. The third property is independence of initial conditions, that is, ergodicity. In the remote past, over time, the more remote a past age distribution becomes, the less impact the form of that past distribution has on the shape of the current age distribution. Similarly, the same factors that cause the transient effects of an initial age distribution to disappear from the stable population will also operate for any time path of the fecundity and mortality rate. After a suitably long period, the effect of an initial age distribution is swamped by the cumulative effect of the age pattern of vital rates. This means that the age distribution of any closed population is entirely determined by the most recent survival rates. The fourth property of population is the effect of fertility and mortality on age structure. Fertility differences usually have a far greater impact on current age distribution than do mortality differences. This is because the role of fertility in shaping age distribution is simpler than mortality because fertility operates in a single direction, starting with the newborn age class 0. Mortality differences, on the other hand, have only second-order effects on the age distributions because mortality tends to concurrently change all cohorts, and thus it has a minimal effect on the immediate age distribution. When mortality changes in a gradual and monotonic fashion, the age distribution tends to change continuously and therefore closely reflects current conditions. The fifth property of population involves changing schedules but unchanging age structure. There are several instances where a change in vital rate schedules are not reflected in the age distribution. For example, if when two populations are characterized as exhibiting equivalent differences in birth and death rates, this means that a change in the birth rate in one has the same effect on age structure as a change in death rate in the other. A second example where there is no change in age structure following a change in vital rates occurs when only survivorship schedules are changed. If survivorship in all ages were to be uniformly reduced by a constant fraction, although growth rate would decrease, this would not result in a change in age structure. Although extreme and hypothetical, this example helps explain why relatively inconspicuous changes in age profiles may occur despite heavy mortality differences across populations. A sixth property of populations involves determinants of age structure. The age structure of closed, stable populations is an outcome of four interconnected, mutually affecting factors. Birth rate determines how many individuals are entering the population as newborn. If birth rate is high, the fraction in the first and other early age classes will be high relative to other age classes. Conversely, if birth rate is low, the fraction in younger age classes will be low relative to older age classes. Age-specific mortality, which determines how many individuals survive to each age, and consequently the ratio of one age class to another, is a determinant of age structure. Age-specific mortality determines population death rates, which, along with birth rates, determines population growth rate. Net maternity is a determinant of stable age structure as it determines the contribution of birth rate to population growth rate, where age-specific reproduction is weighted by age-specific survival. Population growth rate, which is an outcome of the pattern, level, and timing of net maternity as it relates to intrinsic birth rate relative to intrinsic death rate, shapes the age structure by skewing the age structure towards youth when growth rate is high, and shifting the age structure towards the older age classes when growth rate is low. Here I show the effect of growth rate on age and stage structure in a Drosophila population. Here is an age pyramid with frequency on the x-axis in age and age on the y-axis. We have females on the left and males on the right, and this is a replacement level growth rate, or R equals 0. Here are the pre-adult and adult proportions. This skew is heavily towards the latter, which is to say the adult stage. So as growth rate decreases further, we have R equal minus 0.01 and here minus 0.03. You can see that the adult population proportion increases relative to pre-adult proportions. However, as the intrinsic rate of increase becomes positive, you see that the pre-adult population begins to predominate relative to the adults. So by the time R equals 0.2, a very high rate of increase, there are very few adults in proportion to the proportion of pre-adults in the population. A seventh property of populations involves the effect of reproductive timing on intrinsic rate of increase, R. There are three interrelated effects of R owing to shifts in reproductive timing that become easier to understand if viewed as the effects on two components of the intrinsic rate of increase, that is, birth and death rates. The shift in reproductive timing shifts the highly fecund females into younger age classes. A change in the fraction of the population in the highly fecund age classes will, in turn, alter the age distribution due to the effect of this age shift on the population growth rate. This means that the effect on birth rate of a decrease in the age of first reproduction is self-reinforcing. Because of modified population growth rate due to the shift in age structure, and because individuals in different age classes usually have different probabilities of dying, the change in age of first reproduction changes the frequency distribution of population members in different death risk groups. In short, a change in developmental time alters the intrinsic birth and death rates in a population owing to age shifts and age class weightings of the vital schedules. Since peak fecundity usually occurs in younger adults, a decrease in the age of first reproduction will increase intrinsic birth rate, B, substantially in growing populations. On the other hand, a shortening of developmental time will increase intrinsic death rate when mortality is greater in young individuals than in old individuals, but when mortality is lower in the young than in the old, the intrinsic death rate will decrease. An eighth property of populations is the speed of convergence of a population to the stable state. The rate of convergence of a population to a stable age distribution and a fixed growth rate is determined by the following general principles. For a fixed value of net reproductive rate, the speed of convergence increases as the mean of the net maternity function decreases. For a fixed shape of net maternity function, the speed of convergence increases as the value of net reproductive rate increases. In other words, the higher the rate of increase, given the same pattern of reproduction, the faster the population will converge to stability. The speed of convergence to stability depends not on the shape of the net maternity function, but on the shape of the stable maternity function. The smaller the mean of the stable net maternity function, the faster the speed of convergence. The final population property I cover in this module is population momentum. Like physical objects that have a tendency to continue moving once in motion, increasing populations have a tendency to continue growing, which is referred to as population momentum. It is the extent to which a population continues to change in size after it adopts replacement level rates of mortality and fertility. The momentum of a population can be regarded as the opposite of the intrinsic rate of increase, which indicates the growth rate implicit in a set of vital schedules and independent of initial age structure. In contrast, population momentum describes the growth potential due to age structure alone. The population momentum concept is illustrated in this figure for a stable population of Drosophila melanogaster, subject to birth rates that confer population growth. On the bottom we have time, and at the top we have population number. With the population growing from around 65 to 100, at which point we impose a birth reduction equivalent to replacement level growth for the long term. The initial response is a dearth in total number because the eggs are no longer being laid. However, population numbers recover as the pre-adults in the pre-reduction population mature and begin laying eggs. But as it turns out, there is a momentum from these young adult females that adds to the population to a replacement level population that is greater than the population number at the time of the birth reduction. The momentum is due to the disproportionate number of younger females now entering reproductive ages relative to the age structure of the long-term replacement level population. Here I show the stage structure of the fruit fly population before the birth reduction, when growth rate was high. It contained a very tiny proportion of the population in the adult stage. However, after the birth reduction, the adults were well over 70% of the total population. The excess adults account for the momentum is evident in the graphic during the period when time t equaled 10 to t equaled 20. I will end this module by running through a checklist of the basic properties of populations I just described. These include the age structure transients, convergence to stability, independence of initial conditions, fertility and mortality effects, changing schedules and unchanging structure, age structure determination, reproductive timing effects on R, speed of convergence, and population momentum. This ends this module of Chapter 5, which is the last module of this chapter itself.